Okay. I know a couple of people are going to be missing today. Please turn in, if you haven't done so already, by the end of class, please turn in that take-home quiz. Now, okay, what we're on right now, we're on section 15.3. And we're looking at these double integrals, except now we're not just looking at rectangles, we're looking at more general regions that we're doing these double integrals over. There are a couple of people that I already knew were not going to be here, and another couple of people, I don't know where they are. Okay, double integrals over what we call general regions. All right, and we basically have two kinds of these regions, type 1 and type 2. And the type 1 is where we can draw a vertical line through the region and it stays within the region. So we can have something like this, curvy line here, a curvy line here, and say here is where x is equal to A, here is where x is equal to B, but we can draw this vertical line here up through the region and stay within the region. And with this, we want to integrate first with respect to y. All right. And then the type 2 region is where we can draw a horizontal line, and it'll stay entirely within our region. So we could have something like this here and this here, and so we can draw a horizontal line and say we're going from y equals c to y equals d. Now with these, we want to integrate first with respect to x. With respect to x. And sometimes sometimes a region is both type 1 and type 2, and we can choose which one to do. One may be easier to do than the other, and we had an example with that. So you can pick and choose if it's both. All right. So let's go on to next example here. And we want to evaluate the double integral over d of x times y dA. Now, here, what is our D region here? Where D is the region bounded by y plus 1 equals x, and y squared equals 2x plus 6. Okay? All right. Now, what we have to do here is we have to figure out, well, where these are going to be two graphs on the xy plane. Where do they meet? And we've already done this before with a couple of examples. Find where they meet. And then we also want to sketch a rough sketch of this D region. So let's see here. There's a couple different ways we can do this. I'm going to want to use substitution no matter which way I go with it. Any suggestions, or I'll just go on and start it? Okay, so we have that x is equal to y plus 1. So why don't I, in the second equation, let's just plug in y plus 1 for x. So plug in y plus 1 for x. So what do we get here? So we get y squared equals 2 times y plus 1. So I'm just going to go ahead and write that as 2 times y plus 2 plus 6. All right? Okay, that's a quadratic, so let's get everything over to the left side. So that's going to be y squared minus 2y minus 8 equal to 0. And let's see, I think that's going to factor. Two numbers multiplied by minus 8 add to negative 2 would be 2 and a negative 4. So this does factor as y plus 2 times y minus 4 equal to 0. So my y values where they meet are negative 2 and positive 4. All right. Now, we want to then get what are the corresponding x values, because we want to put these 2 points on our sketch. So the corresponding x values, well, what happens here? When y is equal to negative 2, we have negative 2 plus 1 has to equal x. I'm just plugging it into, say, the first equation, and I get that x is equal to negative 1. And then when y is equal to 4, let's plug that in. We have 4 plus 1 equals x. So x will be equal to, yeah, right. X will be equal to 5. Thank you. All right. So let's do a rough sketch then. Because if you don't do a rough sketch of these, you have a really good chance of messing things up when you do the integration. All right. So let's see. The 2 points that they meet, the one is, okay, x is negative 2, y is negative 2. I'm sorry, x is negative 1, y is negative 2. So negative 1, so that's a point right down there. And so let me mark that, minus 1 comma minus 2. And the other one was y is equal to 4, x is equal to 5. So let's go 1, 2, 3, 4, 5. 1, 2, 3, 4. So we have this point here, x is 5 and y is equal to 4. All right. Now let's see here. Basically, we can, well, let's first of all do the straight line. We have y plus 1 is equal to x. If I isolate y, that's y is equal to x minus 1. So basically, that is a straight line. If the intercept is negative 1, so that's going to be a straight line here that, okay, good, sort of like a straight line, that goes through those 2 points. Now, the other one is y squared equals 2x plus 6. All right, this is going to be a parabola. However, it's actually going to be a sideways parabola. Or a parabola oriented in the x direction. Now for this, okay, we can do some points, and actually one thing I want to see is, well, what happens when y is equal to 0, let's just get a couple of points on this and I can sketch it in. When y is equal to 0, we have 0 is equal to 2x plus 6, so therefore x is going to be equal to negative 3. So let's put that point here. So we have minus 2, minus 3. So therefore this is going to be on the parabola. So let's just start to get a parabola going there. And then another thing, let's see, when x is equal to 0, y squared is equal to 6. So y is going to be equal to plus or minus the square root of 6. Let's see, well, that's going to be somewhere between 2 and 3. Let's just put it that way. We don't have to be exact here with this thing. So somewhere between 2 and 3 is going to be right there. So let me just kind of roughly draw the remaining part of our parabola where I'm just connecting those points. So that's part of our sideways, and of course it continues out like this in the other direction. So it's real important to do, it doesn't have to be a real a real detailed sketch, but you have to have a basic idea of what these two curves look like. And you certainly need to know where they cross each other. So this is my region. All right. Now let's look at this. Is this region, first of all, let's ask ourselves this. Is this a type 1 region? Can I draw a vertical line that stays strictly within the region? Yeah, it is. It's a type 1. But let's also ask ourselves, is it a type 2 region? Can I draw a horizontal line that stays strictly within it? Yeah, it's a type 2 also. Now this is the case here where let's decide which one is easier to do, all right? Now, if we do this, let me play devil's advocate here because we're not going to want to do this as a type 1. If we do this as a type 1 region, okay, remember we've got to integrate from the bottom part to the top part for the y. So that means over in this area, we'd be integrating from this bottom part of the parabola to the top part of the parabola. But then when we move over, say, to the right, towards the right part of this region, we would be integrating from the straight line to the top part of the parabola. So if we were to do this as a type 1 region, we would have to divide this up into two integrals. We first have to be integrating our y from this bottom curve to this bottom curve, and then we'd have to be integrating our y from this straight line to this top curve. All right, so it would be something like this. Okay. Yeah.
Why do you I don't get why
Okay, you don't get y. When you have to do bottom to top, right? Let's look at the left-hand portion of this. What consists of the bottom curve over there on the left? The negative part of the parabola, right? Okay? Because look at this, this parabola is y squared equals 2x plus 6. Let's do the square root of both sides. So y is equal to plus or minus the square root of 2x plus 6. Over here, this part that's above the x-axis, this is y equals the positive square root of 2x plus 6. Right? It's positive. This lower part of the parabola over here is y equals negative the square root of 2x plus 6. So if I were to, and now let's go over to the right. What's my bottom curve on the right? It's this one, right? The straight line. That's my bottom one on the right. And so what's that? That's y equals x minus 1. All right. So if I do it as a type 1, I have two different bottom curves that I have to take into account. But I'm not just, okay, if I did it as a type 1. All right, so here, let's just see what it would be. I'd have to, on the left side, I'd have to integrate from y equals minus square root of 2x plus 6 to my top curve with y equals plus the square root of 2x plus 6. What is my function here? It's x times y. This would be dy, all right? And then what are my x values for this part here? See, I'm basically dividing this whole thing up into these two parts. My x integration would start with, what is this, -3, and go to, I think my x value here is -1. So it would go to -1, and that would just give me that first part. But I need to integrate over the entire region, so then I have to put this other part here. Now my bottom curve or line is y equals x minus 1. My top one here is y equals the positive square root of 2x plus 6. X times y is my function, dy. And then this time I would start integrating my x at the -1 right here and take my x all the way up to the 5. So I'd have to do two separate double integrals if I chose to do it this way. I doubt if many of you are going to choose to do it this way, but you'd have to if you view it as a type 1 region. Are you okay with this?
I get it, but it's confusing. Like, where's the part?
That's why you have to draw. That's why you have to draw your functions. And it's vertical. You start at the bottom one, you go to the top one. Yeah. Now we're not going to do this as a type 1. Then we're going to do it as a type 2. Okay, with the type 2, we're just talking about. Okay, we're going to integrate along this horizontal line for a type 2. And notice with type 2, my curve on the left is always going to be the parabola. My curve on the right is always going to be the straight line. So I only have to do one double integral. So it's easier to tackle this as a type 2. But now we have to make sure, we have to have that drawing so we get the correct limits of integration. All right. Now, with the type 2, we have to integrate first with respect to x. With respect to x. In fact, okay. So we're going to have integral here. Now, x here, let's look at our diagram here. What do we have here? Ooh.
Would it be -3 to 5?
No. Let me redraw this thing because it's too busy as it is. I need to, it's got too much stuff on it. Okay. We found that they meet at -1, oops. What did I have here? -1. I didn't even draw that thing right. -1, -2. All right. And then they met at 1, 2, 3, 4, 5, 4. So we first of all have our straight line here. Let's see, that is y equals x minus 1. So we're going to have our straight line here. And then our parabola, we found out it cuts in at -3 here. And then goes up like this, all right? And this is y squared is equal to 2x plus 6. All right, we want to do this as a type 2 from here to here. Now, for a type 2, we're going to first do it with respect to x. That means I've got to find out where x is starting on the left and where x is finishing on the right. So I need to rewrite this parabola as an equation of x equaling something of y. All right? So it's y squared is equal to 2x plus 6. So let's isolate x. So we have y squared minus 6 is equal to 2x. And let's then divide by 2. We get that x is equal to y squared over 2 minus 3. So that's our x for type 2 starts on the left at y squared over 2 minus 3. We have to rewrite this. So we have y squared over 2 minus 3. And then where does the x end on the right? Well, x ends at the straight line, which is x equals y plus 1 when I isolate the x. So here, my upper level of integration for the x is going to be y plus 1. And then we put our function, which was xy, and we're first integrating with respect to x with type 2. And then let's put our outer limits of integration. Now, here we have to look at y going from what number to what number? Okay? Yep. Our lowest number of y here, we're going from -2. But our top number for y here is the 4 from that point right there. So y goes from -2 to 4. Let me put this in also. And x goes from y squared over 2 minus 3 to y plus 1. So my outer limits here then are going to be -2 and 4, and that's for my y. All right. So this is the first hurdle you have to get across, is setting up the double integral correctly. All right, remember we're always just going to have numbers here on the outer integral limits. So we just have our -2 and 4. Okay, now we can try to evaluate this thing. Okay, we go from the inside out. So with the dx, we're treating y as constant. All right? So the antiderivative of x times y is our constant, is going to be x squared over 2 times y. The y just sticks around as a constant. And now I have to put my limits here. Now I do recommend, this is our lower limit for x. So put x equals y squared over 2 minus 3 down there for your lower limit. Our upper limit is x equals y plus 1. And then we're going to have to evaluate that. That's our inside integral. On the outside, though, we still have -2 to 4 dx. All right. dy, thank you. Gosh, yeah, dy. All right. So now let's evaluate that inside part. So here we always have some, possibly some fun little algebra stuff to contend with, I'm afraid. And we definitely have that with this problem. Okay, so I first have to, so I have x squared y over 2. I first have to plug in y plus 1 for the x. So that gives me, let's put in the y here, and then in parentheses for the x, I'm going to put y plus 1 squared, and that's all over 2. Then I minus, and then I have to put in the bottom part, so I'm again going to have just the y. And then in parentheses for my x, I'm going to bite the bullet here, and I have to put y squared over 2 minus 3 in parentheses squared. All right. That's the evaluation, and of course we still have our outside integral minus 2 to 4 dy. Okay, so the next challenge is not messing up on the algebra or figuring that out there. All right, so let's see what we can do here. Let me write the minus 2 and 4 here. So let's FOIL that y plus 1 squared. So we have y times y squared plus 2y plus 1, and that's all over 2. And then we have our second part, minus y, and then let me FOIL this thing out. Be careful with FOILing this out here. So we have to square the first part of it, so that's going to be y to the 4th over 4 when we square that. Then we have to do minus 3 times this, minus 3 times that to get our middle term. So that's going to turn out to be minus 3y squared when I combine those two. And then my last term is minus 3 times minus 3, that's a plus 9. And all of that's being multiplied in the front by minus y, and that's all over, yeah, that's right. Hold this, I'm forgetting something here. X squared, oh yeah, I did forget this here. Yeah, on the top one up above, that whole x, that's all over 2, so I needed to put that over 2 right there, and then I need to put this also over 2, so I'm just going to put the 2 in the denominator right there. Okay. All right, then let's see what we get here, minus 2 to 4. I think what I want to do right off the bat, why don't I just take this 1/2? Because I have a 1/2 in both the terms. Yes? Wait a minute. Isn't it? We have, it's, okay, it's x squared y over 2. So I have I'm subtracting minus y. Here's my x squared, and I have to have it over 2. Yeah, it has to be over 2. All right, I'm going to bring this 2 out. Let's just do that. And so we have to then multiply here. So I have y, okay, I have y to the 3rd plus 2y squared plus y. And then, unfortunately, here I still have that 4 in the denominator. So let's distribute here. We have minus y to the 5th over 4, a double negative, so that's a plus 3y to the 3rd, and then a minus 9y. Okay. Close parentheses, dy. Okay. Let's see. Are there any? Let's look for terms I can join together. A y to the 3rd I can join together. A y I can join together. So let's get this as minus 2 to the 4th, 1/2 times. All right, and let's put them in descending order of power. So we have a minus y to the 5th over 4. And then the next power is y to the 3rd. So that's 3 plus 1. So I have 4y to the 3rd. And then we have a y squared plus 2y squared. And then I have to combine the two y terms, and that'll give me 1 minus 9, negative 8y, close parentheses. dy. Okay. Now we do the antiderivative term by term, and these are not difficult to do. So we have minus, oops. So we have 1/2. Let's do the antiderivatives. That's going to be minus y to the 6th over 24. This one's just going to be 4y to the 4th over 4, so it's going to be y to the 4th. This is 2y to the 3rd over 3, so that's 2y to the 3rd over 3. And that's going to be minus 8y squared over 2, so minus 4y squared. Oops, get rid of that. And now we are evaluating this from minus 2 to 4. All right. Yes? Yeah, just raise the exponent, divide by the thing. All right. Okay, and now the next fun part, I'm afraid, with this problem is then plugging in the numbers and not messing up on combining fractions. All right. So what are we going to have here with this? 1/2, oh boy. Let's see if I can follow what I've got here. Okay, let's see. 4 to the 6th power is the same as, what is that going to be? What's 4 to the 6th power? Is that the same as 16 to the 3rd power? Has anybody got a calculator? 4,096. Is that it? 4,096? Is we got a verification? Is that what it is? Okay. So that's minus 4,096. So we have a minus there, and that's over 24. Okay. And what's 4 to the 4th power then? That's going to be 16. Isn't that 256? 256. And then let's see, 4 to the 3rd power is 64. So this is going to be 2 times 64, what, 128 over 3. All right. And then minus 4 times 16, that's going to be minus 64. Okay. And, oh, I love this problem. And then we have to do a minus, and then plug in a minus 2 down here. So let's just ask ourselves, what's 2 to the 6th power? That's 64, isn't it? Yeah. So this is going to be minus 64 over 24. And then 2 to the 4th power is 16, a positive 6. Minus 2 to the 4th power is a positive 16. Minus 2 to the 3rd power is what, a negative 8. So that's going to be negative 8 times 2, 16 over 3. And then minus 4 times a positive 4 is going to be a minus 16. Yikes. All right. Okay. Why don't we let's just combine the whole numbers first of all. And somebody can help me with this if they would. 256 minus 64, that's 192, all right. And then, now the thing, these whole numbers cancel out here. The positive and negative 16 will cancel out, all right. So with my whole numbers, I have 192. Let's combine these two fractions here that have 3 in the denominator. So that's going to be 128 plus, what's 128 plus 16? That's 144, isn't it? Plus 144 over 3. So that takes care of these two. So the only other thing I have left, here are these two numbers. So this is going to be a plus 64. So, Jordan, what's going to be negative 4,096 plus 64? Negative 4,032, and that's all over 24. All right. Does 24 divide into 4,032? So this here is negative 168. All right. And 3 divides into 144. What is that? 48, isn't it? 3 times 48? Yeah. Okay. So what do we have? We have 1/2 times, okay, what's 192 plus 48? 240?
That equals 72. The whole thing.
The whole thing minus the 168 is 72. And then finally, 1/2 times 72 is equal to 36. So I think on the next step, I definitely want to have maybe 2 or 3 of something just like this.
Yeah.
All right.
The limit being 1 and 0.
Yeah. Yeah, let's have at least 3 of these. All right, so ugly, I'd be the first to admit it's ugly. I don't like doing arithmetic like this personally, but sometimes you just have to do it. So that's what we get. We get a nice 36 as our answer. Okay. All right. Let's do one which is a little bit more user-friendly than the last one. All right. Okay, find volume of solid that's bounded by x plus 2y plus z equaling 2, z equaling 0, x equaling 2y, and x equaling 0. All right. So we're definitely going to need to be drawing a diagram here to figure out, oh, wait a minute. Again, that's it. That's all we're trying to figure out. Okay. Now, just a general question here. This first equation here, that's the equation of a blank. Of a plane, yes. Equation of a plane. Remember, we have the coefficients times x, y, and z equaling a number. That's a plane. All right. Okay. What we have to do is figure out, first, the region in the xy plane we will be integrating over. All right. Now, what do we have here? First, let's see. First of all, we're told, what are our bounds here? We're told that one of our boundaries is x equal to 0. So x equal to 0 is along the y-axis there. So that's going to be one of our boundaries. The other one that we're given is the straight line x equals 2y. So that goes through the origin here, and it has a slope of 2. So it's going to look something, ooh, that probably doesn't have a slope of quite 2. But anyway, that's x equals 2y. All right. Well, we have to close this off. Now, we're also told that our bounds are z equals 0, which occurs on the xy plane. We have this upper bound, though. We have that x plus 2y plus z has to equal 2. But we're also that intersects. So we want to ask, where does this intersect with z equaling 0, which is another one of our boundaries? How can I figure that out? We want to have z equals 0. This is a plane of some kind, all right? It's going to be coming through it's going to be slicing through the xy plane. It's going to be going up at an angle of some kind.
So when you put 0 into 0,
Yes, that's it. Exactly. It's as simple as that. Okay, so just plug in 0 for z, and that's going to give us where it intersects the xy plane. Plug in 0 for z, and that line is where it intersects the xy plane. So, of course, what we're going to get when we plug in 0 for z is x plus 2y equals 2. And that's going to be the third line that I put here on my diagram. So let's see what this is. X plus 2y equals 2. That's 2y equals minus x plus 2. I'm just going to put it in, maybe right now in slope-intercept form. So y is equal to minus 1/2 x plus 1. All right. So this is something that has a negative slope of negative 1/2, and it crosses the y-axis at 1. All right, so let's just have a 1 be here, and it's going to cross, I don't know, it's going to be something like this. All right. So this line right here, that's I can either look at it as x plus 2y equal 2, or in the form that I put it in, y equals minus 1/2 x plus 1. So, remember our bounds. We have this bound here, we have this bound here, and now this other line has created my third bound for my integrator. Up above here, x, y, z. So I've got this area here, let's see, this goes up on the, it goes here on this, positive on the y-axis, and it's also positive on the x. So it's something like, on the xy plane, it's something like that, some triangle like that. All right. And what we're interested in then, and then what we have is this plane that's coming down somehow and crossing this. So the volume here is going to be, it's actually going to be some kind of what's called a tetrahedron. You don't really need to know that, but that's really the volume that's going to be trapped by that plane and the other boundaries that I'm given. We want to know the volume, so really we just need to look at, I take my top z equation and subtract my lower z equation. Well, my lower z is just 0. So the boundary here, the volume is going to be equal to, first of all, it's going to be equal to my top double integral of my top z, which is going to be 2 minus x minus 2y. That's what I'll call my quote-unquote top z. Because remember, we have x plus 2y plus z equals 2. So therefore, z is 2 minus x minus 2y. And then minus my bottom z. Well, my bottom z is just 0. Because I'm told that it's bounded by z equals 0. So that's my bottom z. And I'm doing this double integral over my region D. That'll give me my volume. The top C minus the bottom C, and then I have to double integrate it. Okay, I got the 2 minus x minus 2y from my one equation that I'm given, that is bounded by that plane. This is the plane equation that I'm given. X plus 2y plus z has to equal 2. What I'm doing there is isolating z on one side to get my formula for z.
Yeah, I get that, but
yeah.
Here.
Because that's my, okay, I don't need to put minus, I'm only putting that there for illustration purposes. My lower z value is 0, because I'm told in my problem to bound, one of my boundaries is z equals 0. So I'm just illustrating here that I put my top z value minus my bottom z value, but I just didn't have to write minus 0, okay, because that isn't going to add anything to what we do. Do you understand that I just put it there for illustration purposes?
Yeah,
well, if we're trying to figure out a volume, right? So we're going to take, so what are part of the things with a volume? We've got to look at the height of something, right? So we have the top part of the height, and we have the bottom part of the height. As part of figuring out our volume. So therefore, this is the z-axis here. All right, the z-axis. In fact, nobody, since I can't write things on the board here, I realize I can't do that. Let me put it over here. For volume, we're going to have the top part of the height. Here's whatever the bottom part of the height is. And this is along the z-axis. So from my equations here, the equation for the top part is what I had just given, 2 minus x minus 2y. That's the top part right there, 2 minus x minus 2y. My bottom part is just z equals 0. So I'm just doing the difference of those two. All right? Okay. All right. Now, let's go back here to our drawing. In fact, let me redraw this region here. Y, x. So we had x equals 2y.
Is that where you have to z equals 0? I'm not.
No, I got z equals 0 from the initial statement of the problem. The problem states it's bounded by that plane and then z equals 0 on the bottom part. That's what it means, z equals 0. So that's where I get it, not just making it up willy-nilly. It's from the problem. All right, and then what else? Then we have this 1 here, and it goes through like this. And this is what? X plus 2y equals 2, or y equals minus 1/2 x plus 1. This is the region here. This is the D region that we are integrating over. So question here, this D region that I'm integrating over, is it a type 1 region? Yeah, it's a type 1. That's fine. We can draw vertical arrows through it, and it's all within it. Now the question is it a type 2? Okay. And it's also a type 2. Either way, I can draw a vertical arrow through it that stays within the region, or I can draw a horizontal arrow through it that stays in the region. Which one do you think would be easier to do?
I think type 2, because then my other equation would be x with 0. I want to throw the other two equations.
Now type 2 is where we go horizontally across. We integrate first with respect to x.
Right. One of them is x.
What's that?
If you're doing type 2, you have to do it as two separate.
Exactly. If we do it as a type 2, so let's look at it, first of all, let's look at it as a type 1. Okay, with type 1, we do the vertical, we integrate with respect to y first. With respect to y first. And with that one, we have a top boundary line and a bottom boundary line that never change in formula. It's the same formula. So we can do it as one integral, all right? Okay. If we do it as a type 2, we would be integrating first horizontally with respect to x. And notice then, if I'm at the lower part of this, my rightmost line is this one. But then when I go up further, my rightmost line is this one. So it's like the other one. It's more complicated. Okay. All right. So we're going to want to use this as a type 1 region. All right. So let's see then. That means we have to go from y equals something to y equals something else. Because we integrate with respect to y first. Now, what are my line equations here that I have here? For my one, I have x equals 2y, and for my other one, I have, well, I've got it either as x plus 2y equals 2, or y equals minus 1/2 x plus 1. All right. What's my bottom one going to be? My lower one going to be here? Yeah, it's going to be y. I have to, instead of having it as x equals y over 2, I want to isolate y equals x over 2. That's going to be my bottom one. Now, my top one is the one that I had already rewritten as y equals minus 1/2 x plus 1. That's my top one. All right. So let's get that first integral set up. Where the bottom one is y equals x over 2. My top one is y equals minus 1/2 x plus 1. Now, in this case, there isn't any function that we really just have the function 1 here that we are integrating. So let me whoa. Sorry, I'm never mind. Cancel whatever I just said. We're integrating 2 minus x minus 2y. Gosh. All right. And of course, we don't have to have the minus 0. Now we're going to do the y first, integrate first with respect to y, and then we do the dx second. So with the dx, what are my ranges on x going to be in this region? Yeah. Let's see, what was this point here? This point here was, did I mark it down? I don't think I actually marked this point down, did I? Where do these two things meet here? 2y, let's see, where do they meet? The one is x equals 2y. The other one I can write is x equals 2 minus 2y. So I can set the x's equal to each other. 2y is equal to 2 minus 2y. Is that right? Something seems wrong. Something seems goofy here with this. 2y, x equals 2 minus 2y.
No, that's what I know.
Yeah, that's right. Okay, that's right. Yeah, 4y is equal to 2 then. So y is 1/2, and x then is 1. Plug in 1/2 here, x is equal to 1. All right. Okay, so they meet here. I should have put this in earlier. They meet at 1 for the x and 1/2 for the y. All right. So if I'm integrating then from x, my x goes from 0 to 1. All right, so I've set up my double integral here, so now we just evaluate it. This, frankly, this whole first part is the hardest part of this kind of problem. It's just getting that region down and determining which is best to do in type 1 and type 2. All right. So let's see, we want to integrate this, first of all, with respect to y. So I'm going to treat x as constant. Okay? So what's my antiderivative going to be here? 2y minus x is a constant, tack on y, minus 2y is going to be minus 2y squared over 2, so minus y squared. And then I'm evaluating that. My lower one is y equals x over 2. My top one is y is equal to minus 1/2 x plus 1. And then my outer integral is 0 to 1 dx. Okay, this one has some algebra. It's not quite as daunting as the last one, but let's figure it out here. Let's do the upper one. So we have 2. In place of y, I'm going to put minus 1/2 x plus 1, minus x, and then in place of y, minus 1/2 x plus 1, minus y squared, so I'm going to have minus 1/2 x plus 1 squared, and then minus, and let me just put this all in parentheses here, so now I have to plug in this x over 2. 2 times x over 2 is x, minus x times x over 2, that's going to be x minus x squared over 2, and then minus x over 2 quantity squared, like that. All right, and then this is all going to be from 0 to 1 dx. Well, let's see what we get here. Let's see, from this first one, what do we have? 2 times minus 1/2 x, that's going to be what, minus x? 2 times 1 is plus 2. Here we have minus x times minus 1/2 x, what is that? Plus 1/2 x squared, minus x times 1 minus x. And then we have to square this, foiling this, so I have minus, and then it's 1/4 x squared. When I combine the two middle terms, I'm going to get minus 1/2 x minus 1/2 x, and then plus 1. And then what do we have down below here? We have a minus applied to the x, a double minus plus x squared over 2, another double minus plus x squared over 4. Okay? All right. And that's all going to be dx. So now we need to combine like terms. I think a couple things will cancel out. How many x's do we have here? We have minus x, and then we have a plus x, and then another minus x. So I think I just end up with a minus 2x when I combine all the x terms together. Let's look at the x squares, this is, I think we have, for one thing, we have a minus 1/4 x squared and a plus 1/4 x squared, so those will cancel out. And then we have two of these 1/2 x squares, so that'll both add up to an x squared. And then the last thing we have is our numbers, and what do we have? We have 2 minus 1, so that's a 1. Okay, so that cleaned up pretty well, actually. And so that we then have to do the integral from 0 to 1 dx with. Okay. Are we okay so far with this? All right. Minus 2x is going to be minus 2x squared over 2, so that's minus x squared. X squared is going to be x to the third over 3. 1 is going to become an x, and we go from 0 to 1. All right. So in this case, not too bad, because when we plug in 0, we just get 0. So this is going to be minus 1 plus 1/3 plus 1. So those all combine to 1/3. So that's my answer. Okay. Not quite as ugly as the previous problem, but it's still a substantial amount of work that has to be done. Primarily, the integral itself wasn't that bad. The primary thing is setting up this region here, this domain D. That's the thing. Oh, and I'm just looking at the time here, and before Jenna asked me if we're going to have a break, well, let's have a 5-minute break.
Two really great questions about the So for this one, so you get the same limit going in both directions. Because you get 0 to 0 either way if you set x to 0, for example. So you
need a path that gives you a different number.
Okay, so
right.
But wait, can I set x to a constant that isn't 0?
Well, you know what comes to mind here with this is here we have x times y, x times y.
Right.
Why not set x equal to y? That's a perfectly valid path.
Okay. Well,
yeah.
I mean, actually, well, if I can set x equal to y, can I set x equal to anything then in that case?
Like what do you mean by anything?
Well, I mean, can I set just to -1 or something like that? Since we're approaching 0, the reason I didn't do that was because we're approaching 0, 0, so you didn't make sense to set equals to
right.
-1. Oh, but you can still set x equal to y in that situation, even if you can't set it to a constant.
Yeah, right. There's all kinds of paths to 0, 0.
Okay.
There's the ones along the axes, which is probably what you were doing, right? But we got an infinite number of ones, and we can do x equals y, y equals x. That gives us another path.
Or like x equals 3y.
Yeah, right. But that's the easiest one. Okay. You'll get a different number.
Gotcha. All right. Well, thank you.
Yeah.
My other question.
Yeah.
So I don't actually know the take derivative of y dx, where y is a constant here.
Oh, yeah. Okay. Well, let's look at this. Let's just go back to one variable. Let's say we want to get the derivative of 2 to the x power.
Okay.
The formula is 2 to the x times the ln of the number.
Oh, I mean, you mean that's the formula of the
Yeah, if a is a constant, the derivative of a to the x with respect to x is equal to a to the x times the ln of a.
Okay.
Yeah.
Is it something you memorize, or? Okay.
That was in Calc 2. Yeah,
okay.
Somewhere buried in Calc 2 early on.
Okay.
Yeah.
It's several years. That's okay.
I know. So when I wrote up that problem, I thought, okay, I'm gonna uncover a little part of Calc 2 with that problem.
Okay. All right. Well, thank you very much.
You're welcome. Oh, you know I'm not.
I'll do one, that's it. And then you can do another one, just as long as you do one where we set it up right, and then.
I just love playing with you. Yeah. You know, you have me less than this. You should fun that.
Very straightforward. Well, that take-home quiz was way harder than that stuff.
It's a take-home. Something you can take home.
Even the math theory was.
Can be a little bit harder, but you can take it home. You can look up what you need to look up.
Well, take-home test. That was crazy.
Take home. Oh yeah. Oh, there you go. Except, no, I better not. Take home tests are harder.
My
Yeah.
math teacher in high school, we would talk about, we would get together, groups like 10 people, it taking so long to work through them.
Yeah. Yeah. So, not necessarily a good thing having a take home
Well,
test.
now we would love to run and figure out TikTok and start to do that. Okay, you're going to take home quiz, you're going to have that oriented in class, and then I was like, okay, I'll have to take home test. It was the hardest thing I ever did.
It would have probably been a lot easier in class. Yeah. Right. We've only got a couple more things in this section, and then I'm not even going to try to go into the next section today. I'm going to raise the white flag. Next section we talk about polar coordinates. Yeah. Oh, it's not too bad. Actually, these problems here that I just plowed through, those are the worst. Well, if you don't sketch something out, you're going to have some problems. Yeah. Okay. Well, I think I'll have to just get going here with this. Now, so what we've seen here was the last couple of problems. The region was both a type 1 and a type 2 region, and we could have done it either one way or the other, and we selected the way which was the easier way, even though that necessarily wasn't so easy. But sometimes we can have a problem in which, if we want to hope to get an answer, we're going to have to only do it one way. And so there's going to be two of these that I'm going to go through here. So sometimes we need to, quote unquote, reverse the order of integration in order to get an answer. Okay, and two examples. Here's the first one. Evaluate the double integral from 0 to 1, from x to 1, of sine y squared, in parentheses, dy dx. Okay. So this is set up as where you're going to do the integral first with respect to y, and then with respect to x. So let's say, okay, let's do that integral with respect to y. So let's figure out, well, what is the antiderivative of the sine of y squared? All right. Now you can try to do a u substitution, try to do some trig thing. No matter what you try to do, you are not going to get the antiderivative of the sine of y squared. it was very briefly, but I did mention in last semester that there are some functions that you cannot get the antiderivative of using regular, what are called elementary functions, like sine, cosine, exponential function, radicals, things like that. This is one of them. They have what happens here, there's a field of special functions where you determine what this antiderivative is using what are called special functions. So, if as it is right here, I cannot get, doing it this way, with trying to integrate first with respect to y, I can't get anywhere. But I can get an answer if I reverse the order of integration. Or let's put it this way, I can at least get a shot at getting an answer if I reverse the order. So I can at least get a shot at an answer if I reverse the order of integration. Now, I can guarantee you will not correctly get the order of this correct unless you draw a little diagram. So, you must sketch, and this is not a hard sketch, the region D. Now let's figure out what this region is. What is x varying from? X is varying from 0 to 1. What is y varying from? Y is varying from x to 1. All right. So let's see if we can try to draw this out. Okay, x is going from 0 to 1. But here, y is starting at the x value and going up to 1. So let's put a 1 up here for y. So y equaling x is our starting point for the x. So my line that I'm going to draw here is the line y equals x. Let's complete the box here. This here is the point 1, 1. My region that I'm integrating on, is it my bottom triangle or my top triangle?
Why did we put a box?
Why did we put a box? Because either one of these triangles is going to be my region of integration. Look here. X goes from 0 to 1. Y goes from x to 1. So my top values are going to be 1 both ways. So I just drew a box there for y equals 1 and x equals 1. All right? But which one of those two triangles is going to be the appropriate region? What if x were equal to 1/2? When x is equal to 1/2, what does y vary from? Right here, x is equal to 1/2. Y varies from x to 1. Yeah, 1/2 to 1. Where is 1/2 to 1 here? Here or here? Upper or lower? For y? Upper, right. Right here. It works the same with any other value of x. If I'm looking at x equals 1/3, y varies from 1/3 to 1. So here it's going to vary up here. So the triangle here of my region is the upper triangle. This here is my D. All right. Are we okay with that? Figuring out what my region is. Now, with the way we have set it up here, we were going from y equals x going from 0 to 1, y going from x to 1. All right, in other words, we were first integrating with respect to y, and then with respect to x. So I was first integrating vertically like this with respect to y, and then going and integrating with respect to x. All right, I want to now set this up where I integrate first with respect to x and then with respect to y. So with this, with x here, I want to go x goes from what to what, y goes from what to what. I have to set up new limits of integration. Okay, in other words, why not just keep the same old ones? Is that an answer? Is that a question then? Okay, let's look at this first, and then let me try to answer your thing. Okay, if we're first told to reverse the order of integration, that means instead of first integrating with y and then with x, we're going to want to integrate first with x and then for y. Now, this means we have x going from something to x going to something on the inside.
How does that relate to sine y squared?
It doesn't relate to sine y squared at all. It relates to the region that we're integrating sine of y squared over. This is our f of xy. In this case, it's only a function of y. All right? I don't think so, but we're integrating this function over a region. It's just like, what's the relationship between x squared and 1 and 2 for single variables? We're just happen to be integrating x squared over that line from 1 to 2. That's the same thing here. We're going to be integrating this sine of y squared over this triangle. Yes, we will. In fact, let me do this here. Thank you. Sine y squared, right there. Okay, so we're starting first with integrating with respect to x. So we know the triangle we need to use is the upper triangle. So x goes from what value to what value in, now we're going this way. No, x does not go from 0 to 1. Yeah, x goes from 0 to y. This line here is the line y equals x. We could alternately look at it as the line x equals y. So x goes from, here's the 0 value of x. It keeps going across until it hits the line x equals y. So my lower value is 0. My top value is x equals y. Which is completely different than the limit of integration that I had initially. What are my limits for y? Then I have to integrate y from something to something here. Yeah, y is going to go from 0 to 1. So let me rewrite this thing so it looks a little better here. This is our new integral with the orders reversed. X is going to go from 0 to y, and then our function is sine y squared, and this is with respect to x, first of all, and then we're going to do y from 0 to 1 rather, dy. If you don't draw this diagram here, you're not going to be able to accurately figure out, okay, we know we can't, if we go vertically first, we can't figure out what the antiderivative is. So we need to go horizontally. What are my limits here on my x? Well, here we have a limit. First, the bottom one is 0, but when we hit that line over there, my top value is whatever the y value is. Okay. I can guarantee you that you are going to have reversing orders of integration on the test. Yes, Jenna?
I don't know about y equals x, like, to draw that. When we were trying to draw that, how did we know that y equals x?
Okay. Let's see, this is the thing we were given. How do we know we had y equals x? This is what we're integrating over, because this is how the problem was given. 0 to 1 for y, 0 to 1 for x to 1 for y. This is the problem that was presented to us. I'm getting really messy here. That's the problem we're given. Where does y vary from in this given problem? So we can put here y, x arrow 1. Where does x vary from in the given problem? Let's figure out what area represents that. Y going from x to 1. This means y equaling x to y equaling 1. Okay, does that help? And that's where the line y equals x sprung up. Okay, all right. Okay, so anyway, now we have, let me rewrite this again so we can work this problem finally. Here's our new integral, 0 to 1, 0 to y, sine of y squared dx dy. All right. Now this is doable. Remember, we do our inner one first. So what's being treated as a constant for my inside? Yeah, the whole thing, because y is a constant. So therefore, sine of y squared is just sine of a constant. So I can now do an antiderivative here for the inside. I just have a constant, so I just multiply it by x. That's my antiderivative. And then I'm going to put in my limits here. This is as x, lower limit, x equals 0. Top limit is x equals y. And then let me put in my outer integral 0 to 1 dy. Now when we plug in these limits, we're going to have doable, antiderivatives we can get. So now I plug in y for x for my top one, so that gives me sine of y squared times y minus sine of y squared times 0. And we do that antiderivative from 0 to 1. Okay, so second term is 0. So so now I have the sine of y squared, y times y, dy. So how can I do that? Use substitution. And Jordan, what's going to be my u? Yeah. But u equal y squared, du is equal to 2y dy. So therefore, 1/2 du is equal to y dy. All right. Another thing that I'm just going to go on ahead and do, since it's a definite integral, let me just put in my new limits of integration, and actually they're going to be the same. When y is equal to 0, u is equal to 0. When y is equal to 1, u is going to be equal to 1. So in this case, I still have the same limits of integration. So this is 0 to 1 of 1 half, let's see, y dy is 1 half du, and then sine of y squared becomes sine of u. All right, now I can do that. Antiderivative of sine is the negative cosine. So I have negative cosine of u, and I'm integrating from 0 to 1. And let's see. What do we get here? I plug in my 1 here, so I get minus 1 half cosine of the angle 1. And then I have a double negative plus 1 half cosine of the angle 0. Right? So my answer here, do we know what the cosine of 1 is? I don't. All right. And I don't expect you to tell me what it is either. Just leave it as the cosine of 1. But we do know the cosine of 0 is equal to 1. So our answer is 1 half minus 1 half times of the cosine of 1. What quadrant is the angle 1 in? Yeah. Because pi is 3.14. Pi over 2, which is 90 degrees, is what, 1.57. So the angle 1 is somewhere there in the first quadrant. But anyway, this is our answer then. I don't want anything more from just that as our answer. Okay? But at least we were able to get an answer. Let me do one more here, which is similar to this. And again, we are going to reverse the order of integration. And here we're actually told to do that. Evaluate by reversing the order of integration. And what we're told initially is this: from 0 to 1, from 3y to 3, e to the x squared dx dy. This is another one that I couldn't do with this order of integration. E to the x squared is another one of those functions that I cannot, through ordinary means, get the antiderivative of. So we're going to write this then as question mark to question mark, question mark to question mark, e to the x squared dy dx. So this is going to be y equals some question mark to y equals another thing, x equals something to x equals something there. That's what we mean by reversing the order of integration. Now, the only way I can do this accurately is to do a sketch of my region. Now, what happens here? Okay, x goes from 3y to 3. So x, 3y to 3. In other words, x equaling 3y to x equaling 3. Y goes from 0 to 1. In other words, y equals 0 to y equals 1. So what kind of line do I need to draw in here as one of my first things that I'm going to do? Let's see. X goes from 0 to 3. Okay, so we have, let's see, 1, 2, 3. All right. Okay. But that's for the right part of where x goes to. Remember, so x here goes from 3y to 3, which means it goes from x equals 3y to x equals 3. So what other line do I need to draw in here? X equals 3y. Okay? Now, x equals 3y, let's see, I want to try to draw x equals 3y. Well, I tend to like to just isolate y, so if I divide by 3, that's the same as y equals 1/3 x. All right, I can do it that way. Is everybody okay with that? I mean, that helps me to be able to draw it better. So this is something that has a slope of 1/3, so therefore it's kind of a flat line, actually. Something like that. It's not even that much. But this is the line, either x equals 3y or y equals 1/3 x. Okay, so x goes from this line to x equals 3. So why don't I've got that arrow there. And then y goes from what to what? 0 to 1 here. Well, what is this point right here? Yeah, x is 3, and then y is 1/3 times 3, y is 1. Okay, so we have x, so we have y is going from 0 to 1. X is going from 3y to 3. So this is our region here. This is our triangle. Comments before we go any further? So it's this thing bounded here, here, and here. Okay, now we want to reverse the order of integration, so we need to first get our bounds for y. Y equals something to y equals something else. So we're wanting to do it this way first. Integrate first with respect to y. So what are my bounds for y here? What's my lower bound for y? Yeah, 0, right here. You can see y equals 0 is my lower bound. What's my upper bound for y? Yeah, it's 1/3 x. It's this line right here. Y equals 1/3 x, right up there. My bounds for x, well, we can see here my left-hand side, my x is equal to 0 there, and my x goes all the way to 3 here. Okay. And then this is what I now work with, this integral. So you have to draw the diagram. So let's work with this integral here. Let me rewrite it nicely and then let's do it. So x is going from 0 to 3, y is going from 0 to 1/3 x, e to the x squared dy dx. Okay, we work from the inside out. So on the inside, y is our variable, x is constant. So since x is a constant, ex squared is also just a constant. So my antiderivative here on the inside is ex squared times y. And that gets evaluated from y equals 0 to y equals 1/3 x. And then the last part will be from 0 to 3 dx. Okay? All right. So let's plug in the top limit and the bottom limit. So the top limit is 1/3 x, so that's e to the x squared times 1/3 x. And then my bottom limit is just going to be e to the x squared times 0. So I'm not even going to write that. And then this is from 0 to 3 dx. Now, it's just like with the previous one, I can do this antiderivative again using a u substitution. We're going to let u equal that x squared. So du is equal to 2x dx. So therefore, x dx I'm going to replace with 1/2 du. I'm also, since it's a definite integral, I'm also going to replace my limits of integration. This was an error that some of you guys did within the last semester. So, when x is equal to 0, y is also, x is equal to 0, u is also equal to 0. But when x is equal to 3, u is equal to 3 squared, u is equal to 9. So I'm just going to change my limits of integration, reflecting the u. 0 to 9. Okay, x dx is going to be replaced by 1/2 du. And then I still have a 1/3 there that I need to keep in the picture. And then e to the x squared gets replaced by e to the u. So I have here 1/6 times e to the u. And I can get that antiderivative. That's just going to be 1/6 e to the u. My limits are from 0 to 9. Right? So my answer here, I just plug in my 9 and my 0. I give 1/6 e to the 9th power, which is a very big number, by the way, minus 1/6 e to the 0 power, which is just equal to 1. So my answer is 1/6 e to the 9th minus 1/6. Okay. All right. There's only, this isn't, I'm just going to show these two. So I showed two examples of where you reverse the order of integration. Just these two diagrams that I want to show you are just a couple properties of double integrals. Say we have the misfortune, perhaps, of having to integrate over this region here, D. Now you see how D kind of just moves out all over the place. Well, guess what? We can divide this region into one that is a type 1 region and one that's a type 2 region. Notice if we put a straight line through that rightmost part of it, this here is a type 1 area, and that other one's a type 2 area. So I can do this double integral over this entire region D by dividing it up into doing it over the first one plus just doing it over the second one. And then the second thing here is this. This is something we're going to use in the next section. If we are doing a double integral over an area, over a region D, if we just put in a 1 here for our function, what I obtain as my result is the area of that region D. All right? So this is the formula here. Let me put a little asterisk by this thing here while you have everything away that you're going to be using at some point during the next section. So to get the area of this region D, we just do a double integral. You're just using the number 1, and we'll get the area. Okay. All right. I'll shut up. And I promise. And I'll see you on Monday then. Have a good weekend.